Next, substitution reactions. Substitution reactions may be the first kind is electrophilic substitution reactions, and the second type is nucleophilic substitution. Again, nucleophilic substitution reactions are four types of reactions are there, which we are going to be discussing in the further. Right? Nucleophilic substitution reactions. Then first you come to ring isomerization reactions. Ring isomerization. Ring isomerization of benzene derivatives. Right? Benzene or benzene derivative. First you take the benzene. It is subjected to light irradiation. Then this light irradiation sometimes here 254 nanometers of light, or sometimes lower frequency, the higher energy radiations are also. That means we are start from 160 to 240 or 250, 260 nanometers radiation from 160 to 260 nanometers. In that range, it is undergoing the undergoing ring isomerization reactions. First, you consider the we are considering the 254 nanometers. It will leads to the a cross reaction reactions like the products are benzoylene and also fulvene is also the product in this case. This is the lower energy radiation at the lower energy photochemical condition. Fulvene derivative and benzoylene is the main products. At the same time, whenever we are irradiating the benzene at a lower frequencies, it is 162, 200 nanometers. At that region, it gives the mixture of three products, that is benzoylene, next to fulvene, and benzene. This is the benzene. Three compounds are generated when the lower, higher energy radiation. Benzene. At lower energy radiation, we can see the only two products, that is the benzoylene and fulvene. These three products are generally seen, and how these compounds are generated. In the case of when you come into the mechanism, the benzene is subjected to radiation at 254 nanometers. It leads to formation of singlet state of the first excited state. Singlet state of first excited state. How to determine the first excited state? Here the 6 electrons are there. Therefore, 6 molecular orbitals can be generated. These are the bonding molecular orbitals. These are the anti-bonding molecular orbitals. Phi 1, Phi 2, Phi 3, Simply can show like this sigma psi 1, psi 2, psi 3, psi 4, psi 5, psi 6. At the ground state, all the six electrons are filled in bonding molecular orbitals. Whenever you are subjected to irradiation of light with light, the electron is exited from psi 3 to psi 4. Now, this is called first excited state. That is, the electron is exited from psi 3 to psi 4. That is called first excited state. That is called S1 state. It is called S1 state. At that S1 stage, first it is undergoing cross radiation. That means you can. I'm observing another cake structure for our convenience. Right. Now, this pi electron bond will be broke down. Right. And this bond will be broke down. These two carbon electrons are combined together that produce bond, and the diradical system is generated. This biradical derivative or biradical transition state. These two radicals are combined together. That leaves the formation of benzene. The product is like this. They just like to like right. This is the product. Benzene. Now, how fulvene is generated? The fulvene generation, um, somewhat simple arrangement. That is involving here the hydrogen is there. This proton will be moving to here. Is the homolytic movage, right? Now it leads to the formation of two hydrogens are there, and radicals are generated from here and here. Here the this whatever the number you are taking, this carbon and this carbon both can get involved in the reaction. That means the cleavage of this sigma bond, the cleavage of the sigma bond. Therefore, these two electrons are combined together that will form double bond. These two electrons at this carbon and this electron both combined together at the cleavage. You can look at here what is the intermediate generated. Okay. You can see the just imagine the four radicals, tetraradical species. This tetraradical species can lead to the formation of A double bond here is between these two electrons, and between these two electrons, a double bond is generated. This is the derivative of full V. Is the derivative of full V. Now, when you look into the higher energy transition, at a higher energy transition, that means the benzene is excited with higher energy transitions, the range 160 to 200 nanometers. At that case, what's happening when you see this? These are the right. The electron is excited from this psi 3 to psi 5 directly. This is called upper excited state. This upper excited state is S2. That upper excited state is S2. Then that S2 is responsible for the here for the formation of biradical. That biradical is formed like this. This biradical system further undergoing the bond formation between these two carbons. Then it leads to the formation of divar benzene. Can be shown like this also. This is the planar structure. If we come into the this is divar. Right. The benzyl derivatives carrying similarly the benzyl derivatives which are carrying alkyl, fluoro, and perfluoroalkyl. Such kind of groups undergoes the photoisomerization, but it can also lead to the formation of isomerized product. Sometimes the resulting in the positional isomers that these are the derivatives undergoes isomerization that leads to the formation of positional isomers. For example, we have several examples are there. In that, I have taken that xylene derivative. This is the orthoxylene. This is orthoxylene. This orthoxylene is irradiated with the light at 254 nanometers. That leads to formation of metaxylene. Lead to formation of metaxylene. That means it is undergoing first cross addition, and that leads to the formation of there is a formation of bond between these two, right? And here both another radical is generated. Here the CH3 and CH3. In the next step, there is a bond formation between these two carbons by the homolytic interactions. CH3 and CH3. Further cleavage of the bonds. For example, in previous case, 1, 2, 3, 4, 5, 6. Here also I'm labeling 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right. Then it leads to the rearrangement, fusion of C1 and C4 bond, C1 and C2 bond. That means that this bond is undergoing the cleavage. And what's happening will get here. There is a CH3 is here, and CH3 is here, radical here, and radical here. And now C3 C4 bond cleavage. What is the C3 and C4? This is the C3 and C, right? Then this bond will undergo in the cleavage. Then it leads to the that is generated. Look at here, four radicals are there. Now these two radicals are combined together. These two radicals are combined together. That leads to the formation of double bond here. Double bond is generated here. CH3, the CH3. Here is the double. Now this will leads to the this bond. Look at here. 1, 2, 3, 4, 5, 6. Now we'll count it 1, 2, 8. This thing. After the rearrangement, it is a difficult task. The bond is like this. 1, 2, 3, 4, 5, 6. Look at here. That is the rearranged product. Right. This is the isomerization reaction. If you consider 1 comma 3 comma 5 tributyl benzene, for example, this is the benzene, and it is substituted with the tertiary butyl benzene. It is, suppose it is treated as R. R is equal to tertiary butyl derivative, tertiary butyl group, right? It is substituted with the preposition subgroup, right? Now it is subjected to irradiation. Then it leads to the formation of the derivatives. First, it is undergoing the oxidation. Right. Next, the cleavage of this bond and this bond. Cleavage of this bond and this bond. Then it leads to the formation of the intermediate and the position of R. Now it will be gives the rearranged product that R will come to the adjacent position. We get it. Now it is for other may undergoes the other structural ring isomerization that it leads to the Dewar benzene. Dewar benzene is like that. May undergoes these pi bonds are also cross addition. Perfect. This is called first one is the 1 comma 3 comma 5 tri-tertiary butyl tri-tertiary butyl tri-tertiary butyl benzene. It results the 1 comma 2 comma 4 tri-tertiary butyl benzene. Tri-tertiary butyl benzene. Now it leads to the formation of Dewar benzene derivative. Dewar benzene derivative. Now it leads to the formation of Prismine derivative. This is called Prismine derivative. Now these are all these three products. One, two, three. These are three products are ring isomerization products. Ring isomerization products. Next kind of reaction, addition reactions.
Sir, sir, just can I copy it on the upper screen?
Yes, yes.
Sir, 1, 2, 3. Thank
Yes.
you, sir.
Next, addition reactions. This is the simple addition reaction. We know that in the unsaturated system, both unsaturated systems are combined together that produce the adduct. But here are somewhat different case. Here the benzene is the unsaturated system, and this unsaturated system or pi system undergoes the addition reaction with some other molecule. That molecule, there is no pi electrons are involved in this addition reaction. Okay. For example, benzene is irradiated in the this acetic acid solution. Benzene is treating with acetic acid under photochemical condition. First, it is undergoing the cross addition and isomerization that leads to the five-member ring. This is the benzoyl. This benzoyl further reacting with acetic acid, an acylated product will be generated. That means it is undergoing cleavage of this bond that leads to the formation of radicals. The radical is here, another radical is here. Now, it is abstracted to the proton, whatever the CH3, C double bond O, and the H. Right. This will undergo the homolytic cleavage. Now, this will move to here. Later, is the hydrogen, and another radical is there. This is reacting with acetoxide. When both will combine, that leads to the formation of addition product. This is called molecular addition. Here the hydrogen is there. Here O, C double bond O, C. Simply you can see show this OAC will be shown like this. OAC double bond. Right. Similarly, if you take some amino compounds, amino derivatives, that is also undergoing addition reaction. Benzene and the radiation with light at a lower intensity, lower frequency, that is a higher energy radiation. Now it leads to formation of this derivative, this biradical intermediate, which is treating with an cycloamine. Cycloamine. It is transferring of hydrogen radical followed by the stacking of amino radical. Cyclohexanamine radical. Hydrogen is here and the NH cyclohexane derivative is generated. But and sometimes these may be undergoing the rearrangement. That means that may be undergoing the rearrangement. That leads to the formation of this kind of product. That means a mixture of product is generated. If these two are isomerized, due to that reason, a mixture of product is generated. Okay, these such kind of reactions are called addition reactions on aromatic systems. Addition reactions on aromatic compounds. Now, coming to the cycloaddition reactions. Cycloaddition reactions. Now, benzene derivatives undergoing plenty of photochemical reactions with the alkenes. These products are polycyclic, non-aromatic compounds are generated in these reactions. These cycloadditions can be across ortho position, that is 1, 2 cycloaddition reactions, and meta position, that is 1, 3 cycloaddition reaction, that is 1, 4 reaction, that is para addition reaction. That means benzene can undergo the variety of photochemical cycloaddition reactions with olefin that leads to the formation of polycyclic compounds and non-aromatic compounds. These cycloaddition may be carried out, takes place at 1, 2 position. If the 1, 2 position is involving, that such kind of reactions are ortho addition reactions. Ortho are 1, 2 addition reactions. The addition is cycloaddition. 1, 2 cycloaddition. Suppose if it is involving 1, 3 positions, these are called meta or 1, 3 cycloadditions, or it is undergoing the or it is involving the addition at first position and fourth position. This is called para or 1, 4 cycloadditions. 1, 4 cycloadditions. Now, these reactions are again classified into cross-reduction reactions. Cross-reduction reactions. In the cross-reduction reactions, we see like that. In the previous case, we seen that benzene generates the benzvalene. Benzene can generate the benzvalene, right? Now, whenever it is involving in the reaction, it is undergoes the and cross-reduction reaction with the olefin OAC. With OAC, it is interacting with this olefin, interacting with that olefin. That leads to the formation of a simple wedge. Just the fusion is takes place just a minute. This will be undergo this cleavage that leads to the formation of first it is generating the radical. The radical is again. Now this double bond is showing like this OAC. Now these two electrons are combined together. These two electrons are combined together. That leads to the formation of the product. The double bond is added here. This is the OAC and the position of right. That is the product. Look at here. Just simply the breakage of the sigma bond into biradical intermediate. That biradical intermediate is interacting with the this volcanic system that is involving the formation of addition product. Similarly, you can take the benzene. Remember that it copy it. That mechanism is not given in our book. You copy it, right? And the radiation first it generates the benzvalene. Benzvalene is generated. This undergoes the breakage of the sigma bond into biradical intermediate, right? This biradical further undergoing the addition with the CH, CH3, CH, CH3. Now it will be undergoing the bond, right? Now it leads to generation of the bond CH3, CH3. It is the product. Similarly, you can right? If it is a monosubstituted benzene, if the monosubstituted benzene is there, in the case of monosubstituted benzenes are involved in this cross-reaction reaction, you take anisole, it is OCH3. This OCH3. In that case, it generates the Benz value by the cross reduction. In that cross reduction, you indicate here. Now, this is the OCH3 here position. OCH3 position is here. Now, it is undergoing cleavage. It is undergoing cleavage. That leads to the formation of a biradical intermediate. This is the OCH3 is here. A radical is here, and another radical is here. Now, it is reacting with a cyclopentene derivative. That is a cyclopentene. A double bond is here. Homogenetically, bond formation takes place. Then it leads to the formation of double bond forever. This is OCH3 deletion. Then it leads to bond formation. That is the product which is generated. Is the product which is generated. We can also write like this. All carbon rings. Okay, this is the another three-member ring. But here, that methoxy group is attached like this. OCH3. That is the product. Right? This is about the cycle addition reaction. Now coming to 2 plus 2 cycle additions. It is generally seen in the pericyclic reactions. Next class of reactions are 2 plus 2 or pi 2 plus pi 2 cycle additions. Simply, what are the 2 plus 2 cycle additions? Two pi systems are, this is one pi system and another pi system. This pi system, which is with the 2 pi electrons, this is also with the 2 pi electrons, are undergoing the addition reaction in presence of thermal or photochemical condition. That leads to the formation of a cyclic product. This is known as, and also it is a reversible reaction. This is known as 2 pi 2 plus pi 2 cycle addition or 2 plus 2 cycle addition reaction. Similarly, the same kind of reactions that takes place in the aromatic compounds. Aromatic compounds are reacting with olefin derivatives. That leads to the formation of an adduct. That leads to the formation of an adduct. This reaction is simply electron donor and acceptor between the aromatic and olefinic system. Between the aromatic and olefinic system. Here the aromatic system is the donor and olefin is the acceptor. Olefin is the acceptor respectively. This is the benzene which is undergoing the addition reaction with the OCH3, OCH3, then which is irradiated with light. Then it creates the formation of an adduct. Similar, you take the acetonitrile, sorry, propionitrile, multi-addition with this vinyl nitride, vinyl cyanide, then simply a simple adduct reaction, addition reaction. It leads to the formation of an adduct with a cyclobutane derivative. Similarly, the benzene, which is reacting with butene, first it generates the three-membered ring. Again, these two are undergoing electrocyclization reaction. These two pi bonds are undergoing electrocyclization reaction. That leads to the formation of a sequence of 1, 2, 3, 4 cyclobutane rings are fused to each other. Okay, and a double bond is here. This reaction is Regier selective with a totally substituted benzenes. That is, the two substituents in the products are on the adjacent carbon due to the addition of the olefin. Okay, here. This is the anisole, which is treating with the nitrile. This double bond is undergoing the addition. Then that leads to OCH3. The advantage of photochemical reaction is always the strained molecule. That means higher energy, it is unstable at thermal condition. Those kind of molecules are generated. Okay. Suppose the same reaction is carried out with the cyanobenzene. Cyanobenzene with the vinyl stage in photochemical condition. You look at here, both the substitutions are adjacent to each other. This cyano and OS. Both are adjacent to each other. We have already also seen the same kind of reaction with the benzene and malic anhydride. Right. Then it leads to the formation of a diene derivative, cyclobutane is generated. That is simple Diels-Alder reaction can also produce is subject to a thermal heating that leads to the formation of thermal condition. Same is treating in presence of malic anhydride again. Then it is undergoing the cycloaddition at a thermal condition. The first one is the photochemical condition. It is a thermal condition cycloaddition reaction. Then that leads to This is the product. The first step is the photochemical addition reaction. The second step is the thermal addition reaction. Both are 5 to 5 to cycle addition reactions. This is the 5 to plus 5 to addition reaction, but the reaction may undergo supra-antra mode of addition or antra-supra mode of addition. But here thermal condition, the 5 to S plus 5 to S cycle addition, both are suprafacial or both are antrafacial type of additions. But it is geometrically not possible. Only this kind of stereochemistry is possible. That's why this reaction is called Diels-Alder reaction. Diels-Alder reaction. Okay. Next, coming to cycle addition reaction with some triple bonded compounds. Cycle addition reactions with some triple bond compounds. Benzene is undergoes some alkyne derivatives. A triple bonded methyl state. Then it leads to the formation of a unsaturated cyclobutane fused system. Now you can understand that this will be broke down. That means it becomes rearranged. That leads to the formation of cyclooctane octatetraene. Cyclooctatetraene derivative is generated with acetate substitutions, ester substitutions. Okay. That means the triple bonded alkanes are undergoing the addition reaction. They are further undergoing rearrangement that leads to formation of higher membered cyclic systems. Higher membered cyclic systems. You get here benzocaine. This is anisole derivative. A nitrogen heterocyclic is generated on irradiation with light at 254 nanometers. That leads to at this is the addition product. This addition product further undergoing the rearrangement. An 8-membered nitrogen heterocyclic is generated. This is an 8-membered nitrogen heterocyclic with OCH3 derivation, OCH3 substitution, and this is the nitrate substitution. This is azokine, is called as azocyne derivative. Azocyne derivative. Right. Some other cycle addition reactions. Some other cycle addition reactions. That is benzene is undergoing the reaction with the cumene. Is undergoing the reaction with the cumene derivative. Simply we can call it as allene. This is an allene, benzene with the allene react. Allene is undergoing the addition reaction with one particular double bond, that leads to the formation of any one derivative. This is the product, right? If the same derivative is reacting with the trans butadiene in photochemical condition, that leads to the formation of, here the two products are produced. One is the cross reduction product. One is the cross reduction product. This is the cross reduction product. And 1,4 addition product. What is the 1,4 addition product? This is the benzene. We treat it like this first. One, sorry, 4 plus 4 addition reaction. What is the 4 plus 4 addition reaction? This is the force 1,4 biradical, which is like this. These two combined together. These two combined together. What is the product? That is the product. Okay, that is the product. It is called 4 plus 4 cycloaddition product. 4 plus 4 cycloadduct. Next, coming to substitution reactions. Substitution reaction very familiar for aromatic compounds. Electrophilic substitution, nucleophilic substitutions are very generally seen. But when we come into the photochemical substitution reactions, aromatic photo substitution reactions, aromatic photo substitution reaction. Either again, these are two types. We already know that under thermal condition, benzenes or benzenoid compounds mostly undergoing electrophilic substitution reaction. That is a general characteristic property of aromatic compounds. In contraction, great majority of photo substitution reaction on benzene derivatives may be a nucleophilic. Under thermal condition, it is undergoing the electrophilic substitution reaction. Under photochemical condition, majority of the substitution reactions are nucleophilic substitution reactions. Okay, now coming to the first electrophilic substitution reaction. There are few examples, remarkable examples of photo-induced electrophilic substitution reactions. This can be due to the uh, effect of efficient quenching of the excited states of aromatic compounds by the common electrophiles, and also the 5 to 5 star excited states of the arenes are electron donor in electrophilic media, and the resulting radical cations are unreactive towards electrophiles, or unreactive towards electrophiles, right? Generally, these kind of electrophilic substitution reactions are observed when the 5 to 5 star excited aromatic substances are gets quenched by the quencher. Due to the quenching of that aromatic system, it is, if it is in the electrophilic environment, electrophilic solution, medium, solvent, and readily available electrophiles are there. Therefore, it is undergoing electrophilic substitution reaction. For example, here in this case, the benzene is treating with at the medium. In the previous case, also this kind of reaction we are seeing is reacting with malic anhydride. But previously, we are conducting the direct radiation in this under 254 nanometers. But in this case, the light source is the less than 290 nanometers, and the solvent is trifluoroacetic acid. Trifluoroacetic acid is used. And the irradiation that is undergoing the substitution that leads to formation of again. There is no disturbance in the aromaticity of that benzene ring that leads to the formation of phenyl malic anhydride. Product is phenyl malic anhydride is generated. How it is generated? We see the mechanism. It is generally a ground state complex of benzene with a malic anhydride. Whenever we are irradiation, then directly it produces the S1 complex or S1 state of that a simple complex will be generated between the pi systems of the benzene and pi system of the malic anhydride. Then that leads to the formation of its jitter ion. Formation of its jitter ion. Jitter ion means the positive and negative, both charges are in the same molecule. Those are called jitter ions. Those are called jitter ions. Generally, if these jitter ions becomes uh, aligns when the both the charges are adjacent to each other. But this is called a negative charge is here, the positive charge is here. This is called a simple jitter ion. This jitter ion may undergoes the addition reaction that leads to the formation of an adduct, simple adduct. This is already we seen in the previous case, but it may undergoes the proton elimination. The proton elimination is taking place from here. That is the rearomatization. Rearomatization, right? That leads to the formation of this product. The rearrangement is taking place here also is undergoing. It means elimination of water of hydrogen gas that leads to the formation of this product. Simple. Sorry. No. You get here the proton. Now this negative charge is donated to here. This negative charge will be here. That will be donated to this. Whatever the electrons, pi electrons are donated to this proton, that will be rearranged to produce the phenyl malic anhydride product, adduct, or substituted product. In that reaction, irradiation of benzene and malic acid in presence of trifluoroacid that is phenyl saturated. If it is unsaturated, yeah, is there unsaturated is that called malic anhydride. But it is succinic acid. Sorry, it is the spell mistake. Succinic anhydride. The product is succinic anhydride. Right? In the case of after formation, it is suggested that the product arises by the excitation of the charge transfer complex of benzene and malic anhydride. That is undergoing the followed by it is undergoing the protonation of the deuterion intermediate. The deuterion yields the addition product as the major product. Addition product is the major product, right? Now, this is only a few examples are there, photos, electrolytic substitution reactions. When you come into the aromatics and aromatic substances or aromatic compounds, under photochemical condition, majority of the substitution reactions are nucleophilic substitution reactions. Now coming to the nucleophilic substitution reactions. In this substitution reaction, frequently produce a high conversion rate, and the nucleophiles involved usually hydroxy ions, cyanide, and ammonium ion and amines. And commonly leaving groups are alkoxy groups and nitro groups, a halide group and sulfonyl group. Okay. A survey of these reactions suggests that any of the three mechanisms may operate the photochemical nucleophilic substitution reaction. That means the nucleophilic substitution reaction studied under three types of mechanisms, and one is reaction of nitro substituted aromatic compound, aromatic compound. In this reaction, in the thermal nucleophilic substitution reaction, an electron withdrawing group activates the meta position of that nucleophilic substitution reactions toward the nucleophilic photosubstitution reaction benzene derivatives. The reactivity is consistent with the charge distribution calculations for the substrate in the 5 to 5 star, either it is a singlet excited state or it is in the triplet excited state. When you come into example, it is the nitro substituted product. This nitrobenzene derivative, here the X may be any other substrate, that may be a leaving group. X may be a leaving group like alkoxy group or halide group or any other nitro group or sulfonyl group, like that. Right? This nitro group is influencing the substitution here at the measurement of position. Now the incoming nucleophile is Y minus. For example, it is a hydroxy or cyano or amino or amine derivatives maybe. Okay, under photochemical conditions, that will be X will be replaced by Y. It's looking very easy, but when you are studying the mechanism, it is the high energetic reaction. Then it is irradiated the light. First, it produces the 5 to 5 star excited complex, excited derivative aromatic system or starting material. This is the 5 to 5 star excited state. Then which is reacting with Y minus. Then this is attacking at the meta position. It is influenced by the nucleophile. Then at the higher energy state, they accept the pair of electron from the Y, and this pi electron pair will be moving to here. That will be appear as a negative charge. This negative charge is distributed over all 6 carbons in such a way that can show this as a anionic intermediate or meson complex with negative charge. Right. Then which is the derivative for other the negative charge donated to back. This X will be eliminated as X minus. Then it leads to the formation of the substituted product. The electron density in the 5 to 5 star excited state at the meta position is substantially lower than in the ground state. Whenever it is excited state, the pi electrons are excited from the lower energy to higher energy. In that such a situation, that is exhibit in the exist in the 5 to 5 star excited state. At that particular stage, the electron density at the meta position is lower when we compare to the meta position of the electron density at the ground state. Due to that reason, the nucleophile therefore attacks at the meta position of excited state, directly producing the anionic intermediate. This is the anionic intermediate. These two commonly called as anionic intermediate. These two anionic intermediate, which are resonance structures, anionic intermediate subsequently undergoes the elimination of leaving group like X minus that leads to the formation of photonucleophilic substitution on aromatic ring. Some of the examples, we take the same benzene derivative, same nitrobenzene derivative, but the substitution is changed is OC3 whenever it is treated with KCl in the chemical condition. It leads to the formation of nitro nitride. This is up to 44% yield. Right. Similarly, with the dye substituted product, this OCH nitro OCH3 and OCH3 under sodium the alkaline condition that leads to replacement of one of the OH. OCH3 is replacement with OH. Here we have seen several examples. You can understand. Okay, and other kind of derivative, a meta nitrophenyl phenoxyalkylamine derivatives undergo intramolecular photonucleophilic substitution reaction to give corresponding N-metanitrophenyl alkanolamines with good yield. This reaction is known as Photo-Smiles rearrangement. Photo-Smiles rearrangement. Photo-Smiles rearrangement is exam purpose. It is very important. In that reaction, an alkoxy derivative, alkyl amine oxy derivative. This is nitro CH2, some alkyl group and with the amino group. This is called N meta nitro phenoxy ethylamine. Here it is ethyl group ethyl, which is on direct radiation, or sometimes you can use the sensitizer that leads to undergoing the rearrangement of that alkyl group. That is NO2, NH, CH2, CH2, OH. That is amino derivative is transformed to alcohol. Okay, how this rearrangement is takes place? For chemical condition, CH2, NH2, right? Now it is the excited state. It may be triplet excited state. The lone pair of electrons are present here. It will be donated here. Now this will be transferred to here, which leads to the formation of a anionic or zwitterion intermediate. Zwitterion intermediate. The negative charge is here. One side is the NH2, CH2, CH2, and oxygen. It carries the positive charge. This is the zwitterion. Zwitterion. Now for other, it is elimination of this negative charge, elimination of this OH, followed by the elimination of proton from the nitrogen that leads to the formation of the respective product. NH, CH2, CH2, OH derivative is generated. So that is the mechanism. Now, other kind of mechanism. This is the first mechanism, first kind of nucleophilic photonucleophilic substitution reaction on aromatic benzene. Next, second kind, reaction of methoxy substituted aromatic compounds. Reactions of methoxy substituted aromatic compounds. An electron releasing group like methoxy group is the electron releasing group. It activates the ortho and para position by increasing the electron densities at ortho and para positions towards nucleophilic photosubstitution in the aromatic compounds. The orientation cannot be accounted in terms of the charge distribution in the 5 to 5 star excited state of anisole, but it is realized that in terms of those values for the radical cation, flash photolysis studies supports the formation of radical cation from the methoxy benzene on irradiation. Methoxy benzene irradiation. When you consider the ground state of anisole, uh, the electron densities when you compare with the different values is the anisole. When you compare the electron densities here, minus 9.7, 0.97, here it is the 0.21, it is the 0.55, right? Now at the anisole, it is the ground state. Whenever it is excited to the triplet state, whenever it is excited to triplet state, the electron density will be increased to 0.37, and here it is reduced the electron density 0.19. At the para position, it is rising. Sorry, it is reducing 0.75 minus 0.7. Right. At the formation of the cation radical, what are the cation radical is generated in the reaction? Suppose it is the cation radical. At that position, there is a positive electron density here. At the meta position, a positive electron density again is the all cases increasing the is at 0.204. It is also plus 204. Okay. Support of the formation of radical cation from hydroxybenzene on irradiation with the light. The one reaction is explained here. This is the anisole derivative. OCH3. which is treated with potassium nitrate, potassium cyanide, sorry, potassium cyanide on net radiation in presence of metacyanobenzene, or you can use oxygen in place of oxygen, or you can also use persulfate that leads to the formation of cyanation at the ortho position and para position in equal manner. That leads to two different products. One is the orthocyanoanisole and another one is the paracyanoanisole. Okay. When what is the mechanism? When is it an irradiation? Creates the formation of singlet excited state that is undergoing intersystem crossing. That leads to the formation of T1 state. Then involving the electron ejection that leads to the formation of a cation radical. That cation radical is drastically decreases the electron density at two para and ortho positions. Then the nitrile group is attacking. Nitrile group is attacking at a para position. Then that leads to the formation of the bond between the carbon and the carbon bond. Here it is the radical. Again, here it is having hydrogen, right? Then it's right. Next, transfer of another electron. Transfer of another electron. Whatever the ejected electron, it is received here. Then it leads to the formation of anion intermediate, the negative charge, OCH3 will be donated here. The elimination of H plus that leads to the formation of that paracyano product. It is the yield total overall yield is the 61%. 61% yield, but in that mixture, 1:1 ratio of the products are seen. 1:1 ratio of product is genuine. And electron acceptor like dicyanobenzyne, it promotes the radical cation formation. The presence of an oxidizing agent like oxygen or persulfate in this reaction, it is necessary to to conduct the reaction. Only when hydrogen is being substituted, if these two are necessary, oxygen and persulfate. Following some of the examples are we have then chlorobenzene. Suppose the para position is already substituted with the halogens. However, when the anisole derivative is conducted, a photo substitution reaction with the potassium nitrate in a photochemical condition. The 70% yield, it will be, sorry, 90, more than 90% yield, it will be generated. Similarly, if it is fluorine, it will give the same product to 94%. If it is the nitro group, again the reaction is carried out in the presence of oxygen. Then the nitro group will not replace, but at ortho position, substitution is takes place. At ortho position, the product is generated. Okay. Next, last kind of substitution reaction, photo-induced displacement of halogens by inert ions. Photo-induced displacement of halogen relate is right. Right. Here the substrates are the halobenzene, aromatic compounds. It is halobenzene. If we take the bromo, it is irradiated with some enolate ions. It is treated with irradiation in presence of liquid ammonia. Liquid ammonia, not liquor ammonia. Liquid ammonia, tertiary butyl sodium salt of sodium hydroxide, potassium salt of hydroxide, tertiary butoxide. Then that leads to the formation of that substituted product will be generated. That bromine is substituted. Similarly, is treated with a stone under the same reaction conditions that leads to the formation of substituted product. Right. It is actually at the ordinary reaction condition, thermal condition, to produce this such kind of products are some very difficult. Okay, it requires a lot, so many steps to get the product. Then what is the mechanism involved in that? We take the bromobenzene, is involving electron transfer under photochemical condition. Abstract the electron on the reaction medium that leads to the formation of anion intermediate. This is the radical anion. This radical anion undergoes the leaving of the bromide ion that leads to the formation of benzene radical. This benzene radical further interacting with the a carbon ion, that is the nucleophile. How it is generated? We take the acetone. Whenever it is treated with a base like tertiary potassium salts, tertiary butoxide with potassium salt, that is treated with, it leads to the formation of a carbon ion. CH2, CW1, CH3. Here it is having negative charge. It is having negative charge. Then it will get substituted in this position. It will be substituted. Then it leads to the formation of again anion radical. Anion is our literature shows like this, the attacking of this position, and the radical is here. Right. Now the again the electron donated here, that will be proton will be eliminated. Proton will be eliminated, or it may undergoes the, it may interact with the another molecule of benzene, bromobenzene. Then it leads to formation of again the radical anion, the formation of radical anion, or it is involving electron transfer. Then finally it leads to the formation of, that is um, that H minus will be released. That leads to the formation of the keto product is generated. Okay. This is the photo-induced displacement of halogen by enolate ions. Enolate ions is the enolate. How this enolate is generated, I will show you again. Here, how the carbon ion is generated. This is the acetone. Right. That acetone is treated with a tertiary butyl, a potassium salt. This is a base like characteristics. It will be generated a carbon ion. Right. This negative charge is generated here. That leads to the formation of an enolate O minus CH3 CH2. This is the enolate. This enolate is initiating the reaction, initiating the nucleophilic attack. Right. These two are resonance to each other. Both are connected to the tautomeric structures that leads to the formation of structure. Okay. In generalized, you can give this kind of nucleophilic substitution. Just take the generalized structure of benzene, and it is when the iodine is present, is ZH, where Z may be a methoxy group or amino group or some alkyl groups. Okay, on a radiation, it simply replaces the iodine. Simply it replaces the iodine. It leads to the formation of the corresponding products. Sometimes it is undergoing cyclization. Yeah, or C double bond. This is the enolate ion. In place of that enolate ion, that will be replaced. That leads to the formation of this keto product. Further, it is undergoing cyclization. That leads to formation of the following cyclic product. Okay, these are the various kinds of reactions of benzene derivatives under photochemical conditions. Under photochemical conditions. Okay, do you have any doubts? It is the memory-based chapter. You need to read, then only you can remember all these reactions. Otherwise, it is not possible. You just understand the mechanisms and understand the theoretical concept, then only you can remember it. Okay. Then any
Excuse me,
doubt?
sir. Hello, excuse me, sir.
Yes.
Sir, any important question arise from this chapter?
Yeah, so many normal reactions. Here the given name reaction is given. Okay.
Sir, we have to read everything.
Spice rearrangement, Norris type reaction, Petronovich reactions, and a Barton reaction. The next unit, Barton reaction is very important. Diphenylmethane rearrangement, in particularly isomerization reactions of diene systems, and photoaddition reactions and photoisomerization reactions of alpha beta unsaturated carbonyl compounds. Okay, when you open the previous papers, the repeated questions you can see from chemistry. Those questions only repeated every year. Alternatively, those questions are repeated. The same questions you read it. At least you can get the 50 to 70% of the questions you can attempt.
Okay, sir.
Okay.
Okay, sir.
Okay, I'm concluding the session. Thank you.
Thank you, sir.
Okay, sir. Thank you.
Thank you.
Hi.